Next, we want to state the intervals in which the function is increasing or decreasing, and also find any relative extrema. Well, any relative extrema, meaning any relative maximums or relative minimums, occur at critical values. And we now have the second derivative, which will allow us to determine whether a critical value is a relative extrema. So let's plug our first critical value, -1, into the second derivative. So if we plug a -1 in here, we have 2 times a -1 times a -1 squared minus 3, all divided by a -1 squared plus 1, and all that is being cubed. When we simplify this, we get 4 on the numerator and an 8 on the denominator, which reduces to a 1/2. 1/2 is positive, so since our second derivative is positive, that tells us we have a relative minimum at x equal -1. Okay, so next let's plug in +1 into our second derivative, and when we do that, we have 2 times a +1 times a +1 squared minus 3, and then that's all divided by a +1 squared plus 1, all cubed. And when we simplify this, in the numerator we get a -4, and then on the denominator we get +8, so this reduces to a -1/2. Since our second derivative is negative, we then have a relative maximum at x equal 1, and that's by the second derivative test. So now to determine the intervals in which the function is increasing or decreasing, we can think about how these relative extrema divide the number line up, divide the x-axis up into 3 intervals. Since we have 2 relative extrema, it divides it up into 3 intervals. So with a relative extrema, if we think about what's going on with a relative extrema, our function is decreasing before we hit that relative minimum and then increasing after we hit that relative minimum. So our function is decreasing from -infinity up to -1. So we can say that we are decreasing from -infinity up to -1. And then after we hit that relative minimum, our function is then increasing. So we are increasing then from -1 up to +1. Because once we hit +1, we are then at a maximum, and then after we hit a maximum, our function must decrease. So then we are decreasing then from +1 to infinity. So there's our intervals of decreasing to increasing. Next, we want to list the coordinates of any possible inflection points. Inflection points are where the graph changes concavity. Well, the second derivative tells us about concavity. When the second derivative is equal to 0, it means the concavity could potentially be changing. So let's set the second derivative equal to 0. So we're setting 2x times x squared minus 3 equal to 0. Setting the second derivative to 0, when the numerator is equal to 0, then the second derivative function is equal to 0. So setting this equal to 0, we're going to set each factor to 0. We get x equal to 0, and then x squared minus 3 equal to 0. So if we add 3 to both sides, we get x squared equal to 3. Now let's take the square root of both sides, and we have x equal to positive or negative square root of 3. So we have 3 possible points of inflection. So our 3 possible points of inflection would occur at x equal negative square root of 3, x equals 0, and x equal positive square root of 3. Now since we aren't asked to list the coordinates of the possible inflection points, we should plug these x values into our original function, f of x, and get the corresponding function values. And that'll help us when we go to graph it. We will have additional points on the graph. So if I plug a negative square root of 3 into the original function, we get a negative 0.43. So that point looks like a negative square root of 3, comma, negative 0.43. And if you want to pause the video and check those function values, feel free to do so. Then if we plug 0 back into the original function, we get an output of 0. And then the last one, if we plug a square root of 3 into the original function, we get square root of 3, comma, 0.43. as our function value. Next, we want to state where the function is concave up or concave down. Well, our inflection points, our possible inflection points, are where the function may change concavity. So we want to divide the x-axis up into intervals around those possible inflection points. So we found 3 possible inflection points: a negative square root of 3, 0, and a positive square root of 3. So this is going to divide our number line up into 4 intervals. We have negative infinity to a negative square root of 3, and then a negative square root of 3 to 0, 0 to positive square root of 3, and then square root of 3 to infinity. So let's use the second derivative here to test for concavity. So we're going to pick a test value out of each of these 4 intervals and determine what the second derivative sign is, whether it's positive or negative, and then that'll determine whether we're concave up or concave down. So in this first interval, negative infinity to negative square root of 3, I can pick any value in that interval. I'm going to choose a negative 2. If we plug a negative 2 into the second derivative, and you can try this out yourself, plugging negative 2 into the second derivative, it turns out what you should get is that the second derivative is negative. It is less than 0. Since the second derivative is negative, that tells us that we are concave down. We are concave down on this interval, negative infinity to negative square root of 3. Okay, now the next interval, negative square root of 3 to 0, we got to pick a test value out of there. For example, a negative 1 would probably be a good test value. If we plug a negative 1 into our second derivative, and again, you can pause this video and plug it in there yourself, plugging a negative 1 in here, we get a positive value. The second derivative is positive. Since it is positive, that tells us that we are concave up on this interval. So we are concave up from negative square root of 3 to 0. The next interval, 0 to square root of 3. Pick a value out of there, out of that interval. 1 would be a good one. If we plug a positive 1 into the second derivative, what we get is a negative value. Our second derivative is negative. So that tells us that we are concave down on this interval. We are concave down from 0 to square root of 3. And then the last interval, square root of 3 to infinity. Pick a test value out of there. We could pick 2, for example. If we plug 2 into our second derivative and simplify, what we get is that our second derivative is positive. You should get a positive value. So that tells us that we are concave up on this interval from square root of 3 to infinity. So next we want to sketch a graph of the function. I'm going to begin by plotting the relative extrema. So I plotted the relative min and the relative max. We had a relative min at negative 1, negative 1/2, and a relative max at 1, 1/2. So we know that our function at that minimum is going to look like that, and then at our maximum, because it's a maximum, it's going to look kind of like that. Next, what we can do is graph our inflection points. A negative square root of 3, negative 0.43 was one inflection point. A negative square root of 3 is approximately a negative 1.73 if you get a decimal approximation. And then we have 0, 0, and then we have a positive square root of 3, 0.43. So a positive 1.73, 4.3. So just to kind of do the best we can to plot those points on the xy axis. Next, we can connect the points that we have on our graph so far. So we have our relative min, our relative max, and our inflection points. Now let's take a look at what's going on here to check what we have. So we said that from a negative square root of 3 to 0, we're concave up. So here's our negative square root of 3 to 0. So notice we are concave up, and there's our relative min. And then we're concave down from 0 to square root of 3. So from 0 to square root of 3, we are concave down, we open down, and there's our relative maximum. So now the question is, what is going on for the rest of the graph? Well, from negative infinity to negative square root of 3, we have to be concave down. And then from square root of 3 to infinity, we are concave up. Now keep in mind, we do not have any other relative extrema. There aren't any more relative min or relative max. Also, what I want to point out is whether or not we have any more x-intercepts. We certainly cross the x-axis at 0, 0. Recall, to find x-intercepts, we set our function equal to 0 and solve for x. Setting our original function equal to 0, we get that x equal to 0 is our only x-intercept. So our only x-intercept is 0, 0. So as we finish this graph, we can't cross the x-axis anymore. One thing we can do is create a table of values and pick a couple x values and plug into our original function to get a couple more points on the graph. For example, I chose -3. If we plug -3 into our original function, what we get is a -0.3. And then if we plug a +3 into our original function, we get a +0.3. So there's a couple more points that we can plot on our xy axis. So plotting those additional points and connecting, and then let's double check here. We said that we should be concave down from -infinity to a negative square root of 3. So notice how here we are concave down, we do open down, and then from square root of 3 to infinity, we should be concave up. So from square root of 3 to infinity, we are concave up. I do want to point out, if we look at this function, the graph of it, notice how it looks like our function is getting closer and closer to the x-axis as we approach -infinity. Same thing as we approach +infinity, our function is getting closer and closer to the x-axis. What we actually have here is a horizontal asymptote at 0, at x equals 0, because our function is approaching that line as we go both to -infinity and +infinity. And we're going to learn more about asymptotes in the next section.